you can see our goals of this project. First of all, one of our goals is to highlight the application of topology optimization in the aviation industry, to design an assembly between equipment and the frame in a fighter aircraft using topology optimization. Another goal is to showcase the potential of the topology optimization in creating innovative solutions that meet the highest standards of safety. And last of all, to propose an alternative method for using the topology optimization code and provide an example part using this method. By editing Lewis topology optimization code, we will design a model that can be implemented in the frame shown on the left. From figure 1, isometric view of equipment and frame can be seen. In figure 2 and 3, isometric and side view of the design space can be seen. In figures 4 and 5, different views of the design space and its dimensions are shown. Given the fixed location of the equipment, a specific length of connection elements is required to ensure proper connectivity. Figure 6 provides a clear visualization of the location of the force within the context of this project. The exact location where the force is implemented is a critical factor that influences the topology optimization process, and figure 7 shows the ratio of the length of the MATLAB design space in the y-axis to that of the real design space. These percentages will be used in the VBA code. In figure 8, design guidelines for the fastener distances are presented, which specifies certain distances that must be maintained between fasteners to ensure proper stability of the structure. Specifically, there needs to be a distance between 4 to 6 times the diameter between two fasteners. The distance between a fastener and the edge of the design space should be 2 diameters plus 1 millimeter, and the diameter of each fastener should be a diameter. By following these design principles and taking into account the dimensions of the design space, the number of fasteners required can be determined. In figure 8, design guideline. In figure 9, you can see the data entry section. And in figure 10, you can see the results of the calculation section. These figures were generated from an Excel file, and editing the Excel file will allow us to make changes to the MATLAB design space. As shown in figure 7, the equipment site design space percentage is 54%, and this is also reflected in the figure. It is possible to change this percentage, for example, by modifying the corresponding value in our Excel file. In figure 11, when the user clicks on this button, also you can see in the figure 11 there's a button at the top. When the user clicks on this button, it automatically calculates and generates a table of nodes number for XY plane for every Z plane. For 12, which you can also see at the right of our presentation, when the code runs in the Excel file, node IDs, which will stay in the design space, is filtered. In the Excel file, user can see every node ID which stayed inside the design space. When performing topology optimization, it is important to identify the nodes that are located within the design space, as these nodes are the ones that will be considered during the optimization process.
In figure 13, nodes that will come into contact with the stiffener in the center of the frame are filtered. Fixed nodes are essential in our project because there are certain parts that need to be fixed. The macro in figure 14 helps us identify these fixed nodes, which can then be used to ensure that the design meets the necessary structural requirements. By using the identified fixed nodes in our topology optimization, we can create a more accurate and efficient design that meets our specific needs. If the wrong fixed nodes are used in topology optimization process, it can result in unstable or unrealistic designs that do not accurately represent the physical behavior of the structure. Excel macro is used to list the nodes where the force will be applied during the topology optimization. The purpose of this macro is to extract the load nodes IDs and format them correctly to be used in the MATLAB. These nodes, also known as force nodes, play a vital role in the optimization process as they help to determine the optimal distribution of material within design space. By running the macro associated with this Excel file, the force nodes are filtered and listed, making it easier for the user to identify and utilize them in their topology optimization. Accurate identification of nodes is essential to obtain reliable and accurate results from the optimization process. Any inaccuracies in identifying force nodes can lead to significant errors in the final optimized design. The filter radius is a key parameter in topology optimization, as it controls the level of detail and smoothness of the final optimized design. A small filter radius will lead to more detail and fine features in the design, while a large filter radius will result in a smoother design with fewer details. In this slide, you can see the topology optimization results for different R-mean values, both in terms of appearance and faster results. We chose R equals to 1. Penalization factor is another important parameter in topology optimization, as it controls the trade-off between material usage and design smoothness. A higher penalization factor will lead to a smoother design with less detail, while a lower penalization factor will allow for more intricate and detailed designs, but with a potential increase in material usage. In this slide, different topology optimization results for different penalization factor can be seen. After getting the result of the optimization, we redrew our design space in Fusion 360. In figure 24, the load application points and the frame that the fitting is attached to our design can be seen. In figure 25, we drew the design space on top of the STL file to obtain final design. Figure 26 shows the T-spline geometries that are prepared to be subtracted from the design space. These geometries are created based on the void regions in the STL file obtained from the MATLAB. In figure 27, the T-spline geometries are mirrored to obtain a symmetrical geometry. Then these T-spline geometries are removed to obtain our final design. In this slide, we can see the final design views taken from different angles. In figure 32, you can see the static analysis result. Even when a low load is applied, it can be seen that stress is distributed over the part. This is an indication that the part is functioning well and does not have unnecessary bulkiness. Thank you so much for your attention.